That's a lot. Okay? Yeah. So I estimate for the whole semester we may have about 12 lectures. Yeah, I estimate. Yeah. Although in my syllabus I put 14 lectures, but some of the lectures, the material I can spread into other lectures. So we can reduce from 14 to 12. Okay. So the total approximately 12 lectures. 2 of them we will use on this topic, recursive algorithm. So very important. Yeah. All right. Unit 3.1, Introduction to Recursive Algorithms. Yeah. Why recursive thinking is important in problem solving? Yeah. We want to answer this question. Okay? Yeah. So we're used to straightforward, non-recursive thinking in problem solving. Right? Yeah. So usually, recursive because you need to, I hope some of you do not get confused when you do recursion. Yeah. A function call itself, right? How can a function call itself? Yeah. Yeah. It's not hard to understand that. Okay? Yeah. We know inside implementation a function, why a function can call itself, right? Why a function can call itself without causing infinite loop. We worry about the infinite loop. Yeah. Okay. So here, inside implementation, inside the programming language, when you call functions recursively, there is an internal stack created. Okay? So the recursive function push into that stack. So if your recursive function call many levels, that stack could be very deep. If the stack is too deep, what happened? What would happen? Stack very deep. Yeah, because the recursive function, so many levels, large number of levels. Right. Stack overflow, right? Stack overflow. Out of memory. Your memory has a limit, but that stack takes a lot of memory space. And eventually, it will consume all your memory resource, and it breaks. Yeah. So you have the resource issue. Recursive algorithm can consume a lot of resource. If you do not get that overflow, stack overflow, then you can use it. Yeah. But keep in mind, you need to use a lot of resource, memory resource. Yeah. All right. Some problems can be solved both ways, non-recursively and recursively. Yeah. Yeah. While we still use recursive way, right? So there is some problems you can solve non-recursively and recursively. Okay? But if you solve non-recursively, you do not have that deep stack, right? So that's an advantage. Yeah. If you do not use that big, deep stack, you consume some memory, then you release, right? Consume, release. Yeah. So then you're okay. But if you have a big stack, you cannot consume, release, right? You just consume more and more and more. Okay? That's the other disadvantage. That's a disadvantage. Yeah. Recursion. Yeah. But the advantage we will see. Yeah. It's powerful. It is very powerful. We need it. We know its limitation. Right? We know its limitation. Yeah. But we want its power sometimes. Yeah. All right. Power of recursion. Yeah. Some relatively harder problems can, only I put in a parenthesis, can be solved by recursion. Can, no problem, but only Only some people may not agree. Only some people may not agree. So that's why I put that in the parenthesis. Otherwise, I will remove that parenthesis. Okay? People will argue, right? Yeah. But I don't want to argue with those people. Okay? Yeah. So I put that in the parenthesis. Only because you will see, if you do not use recursion, extremely hard. If it's not possible, extremely hard. Yeah, later, we will see that example. Extremely hard. How can you solve it without using recursion? Yeah. All right. Because sometimes you can see the sentence. Yeah. So the reason, because why people question this one, sometimes you can see some sentence like this. Some people claim, okay? Some people claim any problem, if it can be solved recursively, it can also be solved non-recursively. Some people claim that. Okay? Any problem, if it can be solved recursively, it can also be solved non-recursively. Those people claim, but they didn't prove. They didn't prove. We couldn't see the proof. Okay? So that's why we just acknowledge their claim. Okay? Yeah. Yeah. So we may not agree. Yeah. We may not agree with that opinion. Yeah. To that opinion. All right. Yeah. Recursion versus non-recursion. First question, our problem number 5. Calculate the factorial. That's easy, right? Factorial. Based on the definition, it's easy to calculate. Right? Especially when we write a program, it's easy to calculate. Right? Yeah. But here, it's not that point. Here, the point is I want to compare two ways to calculate factorial, recursively and non-recursively. Two methods. Okay? Yeah, two methods. Yeah, let's compare. Method 1, non-recursive way. Straightforward way. Based on a definition of the factorial function. Yeah. This is the definition. Okay? And factorial. Okay? Yeah. So very easy. So we can write our code directly to get this number. Okay? But here, there is an initial condition. 0 factorial equals 1. Have you seen this before? 0 factorial equals 1, right? Yeah, good. So here, let's go back to the intuition. So I mentioned intuition before. Based on intuition, can you get this? Intuition, why is 0 factorial equals 1? Okay? It does not make sense, right? 0 factorial. You get a 1. Does it make sense? Based on my intuition, it's hard. It's also hard. I couldn't understand why 0 factorial equals 1. Okay? All right. Yeah. So, all right. So, we need to justify it. Yeah. The next slide. We need to justify it. It makes sense. It makes sense, but only after you see that formula. It makes sense. Based on intuition, it does not make sense. I agree. It doesn't make sense based on intuition. But as soon as I show you that formula, critical formula, it makes sense. Yeah. All right. Implementation. Easy. One for loop. You can do it. Only one for loop. Okay? Yeah. So I put that for loop here. Okay? So suppose we have a function. Okay? Factorial function. Yeah. Base case, initial case, 0, you'll return 1 based on this. Okay? Yeah. Yeah. Else, so other cases, non-zero, we start multiplication, but our initial value for the answer is 1. Then we put a multiplication in a for loop. In a for loop, I from 1 through n. From 1 through n, we do multiplication. Answer ans equals I times ounce variable. So we get factorial. That's simple. Yeah. Return answer, right? Yeah. Return answer. Yeah. So this is the first solution. Yeah. Very simple. All right. So why we need to convert it to recursive algorithm, right? So you may ask that. For this question, it may not be good, but we want to learn, we want to use recursive algorithms to solve other problems. So this one, we just use it as a, practice, practice a little bit. Okay? Yeah. All right. Now, we look at the recursive thinking, because we need to change a way of thinking. The thinking way is different. So we look at that. Okay. Take recursion view. This time we change our view completely. That's important. Okay? In other words, for this problem, recursive algorithm may not be a good choice, but the most useful thing we want from it, experience. We want to get experience on recursion. So we can use this experience to solve other problems. That's valuable, right? Experience is valuable. Okay? Yeah. All right. Start from this, but now we take recursion view. Okay? So we change our view angle, our camera angle, we change it. So we get different view. Okay? All right. Let's assume the factorial function, we use f of n to represent it. Factorial function. Okay? This is our original problem. Original problem. Okay? We want to solve. All right. When we solve a problem, there is a commonly used strategy. Yeah, I want to talk about the strategy again. Commonly used strategy. We have the experience when the problem size becomes smaller, the problem is easier to solve, right? So our strategy is, can we reduce the problem size? If we find a way to reduce the problem size, then we will get an easier solution. Okay. So that's the strategy we want to use. Yeah. It's a general strategy. Yeah. All right. General problem-solving approach. The observation, the problem size smaller, easier to solve. That's our, foundation. Yeah. Action. Reduce the problem size and connect it to the original problem. Yeah. You need to connect. Yeah. So if you solve a smaller size problem, you can use the result to solve the original problem. Yeah. That's the connection we need. Okay. All right. Here we use one special method, approach, a sub-strategy, decrease and conquer. Divide and conquer, right? You heard of divide and conquer, right? Yeah. So that's actually this belongs to that divide and conquer. But how do you divide? You have many ways to divide, right? Many ways to divide. Yeah. There is a special way to divide. It's called a decrease. Decrease way to divide. Why decrease? Decrease the size by 1. Decremental. Okay? Decremental. Decrease the size by 1. That one. So we just give a special name. Okay? I mean, that's the author of this textbook. Usually you do not see much in other places. In other places, people just call divide and conquer. Why create a new name, right? So this test creates many new terminologies related to this, divide and conquer. Okay? Yeah, so I give you the reference of this decrease and conquer discussion reference. Okay? All right. We need to maintain, when we divide, we want to maintain the same structure. We don't want to break the structure. We want to maintain the same structure. Okay? So let's divide in this line, cutoff line. Okay? That's also decrease. Yeah, decrease, that means you reduce size by 1, right? So we reduce size by 1. So we cut off one element, okay? Largest element. Okay? After you do that, you get a smaller problem, f of n minus 1. Still you get a factorial, but with a smaller size. The size is reduced by 1, n minus 1. Okay? Then you connect, because you need to connect. Okay? So that the solution of a smaller size problem can help you find the solution of the original problem. Okay? So that's the importance of the connection. So the connection is this. Okay? You just multiply your previous solution by n. You get an answer. That's the connection. Okay? This is the recursion view. This is the important recursion view. Okay? Although this question is a simple one, but this view is important. Okay? And later, in many situations, we need to take this view. Okay? Decrease the size, especially, it's very common, especially for recursive algorithms. Most of the time, we decrease the size by 1. So not 100%, but most of the time, we decrease the size by 1. Okay? That's why this view is important. Okay? This experience is valuable. Okay? Yeah. All right. Now, let's look at this formula closely. Okay? I will do some magic. The formula here. Simple, right? Very simple. But I will do some magic. So you see something really impressive. Yeah. So let me do it. Okay. Can we write in this way? F of n minus 1 equals f of n divided by n. You just do division n. Okay? You can do it, right? It's legal, right? If n greater, but n cannot be 0. If 0 you do division, then you cannot. So we assume n greater than 0. Okay? N is an integer. We know it's an integer. Greater than 0. Okay? Then it's legal. Right? It's a legal formula. Right? Okay. No problem, right? Yeah. All right, the magic. Okay, see? Yeah. Take n equals 1. What will happen? N equals 1. That's legal, right? 1 greater than 0. That's legal. Where n equals 1, what will you get? F of 0 equals f of 1 over 1. F of 1, factorial of 1, it's 1, right? 1 over 1 is 1, right? Now, what is f of 0? What is f of 0? The meaning. Is it factorial of 0? Factorial of 0 equals 1. Is this correct? It makes sense, right? From this formula. This formula is correct. Okay? That's the magic. This is magic, right? Because against our intuition. The magic usually, hard to understand, right? What could happen? Here, that's the justification. N factorial, why n factorial equals 0? This is the justification. Very solid justification. Okay? Yeah. All right. Recursive implementation. Yeah. Base case, n equals return 1. Then else, you call the function recursively. Okay? That's simple. That simple. All right. So now we complete method number 2, recursive algorithm. Now, if I ask you to compare these 2 methods just for this factorial problem, right? Not for other problems, just for this factorial problem, which method is better? Can you give me which method is better? Method 2. Oh, I heard method 2. Anyone tells me method 1? Good. Method 1. All right. Any other? Any other? Has confidence? Has some confidence telling me which one is good, is better? 1. Good. I heard another one. Okay. 2-to-1 ratio. Oh, but not just that. The reason is simple. Why method 1 is better? Method 2, stack. Think about memory consumption, deep stack. Okay? That's the biggest problem. Okay? That's the biggest problem. Deep stack. Okay? Method 1 we can solve easily without that stack. Why? We do not use it. Right? So the recursion will usually, it's hard to solve non-recursively. Then we will sacrifice the memory consumption resource, precious resource, to get a solution. To get a solution. Okay? Yeah. Recursion. Yeah. We sacrifice a lot of things to get that solution. Okay? Yeah. So that's why I'll ask you this question. Yeah. All right. We still have a few more minutes. Yeah, let's conclusion. It is an interesting way to solve problems. Well, we take a different view. Okay? So it's interesting. So we do not say it's perfect. Right? It is not perfect. Yeah. Yeah. It's interesting in what sense? Because in some situation, when we have no way to handle the problem, yeah, we just don't know how to find any solution, this one will rescue us. Yeah, that's its value. Okay, that is its value. Yeah. When we really get stuck, yeah, couldn't solve, couldn't go anywhere. So, oh, I saw snowing. Yeah. All right. So let me stop. 10 minutes earlier. So let's go home quickly. Yeah. Yeah, because it could be very dangerous. Yeah, if too late. Yeah. All right. Yeah.